In early 2025, a quiet tremor rippled through the world of physics, not a quake of the Earth, but of time itself. It started with a single tick, a deviation so small it bordered on the unimaginable, 1/4 of a second. The kind of difference that on paper would seem laughable, insignificant, but in the hushed halls of the world's most advanced laboratories, this tiny flicker of discrepancy hit like a thunderclap. Something was wrong. Or perhaps something had always been wrong, and now for the first time, we could finally see it. Modern atomic clocks are the crown jewels of human precision, quiet machines that don't just tell time, but define it. They've reached such staggering accuracy that even the difference in height between two atoms, less than the width of a paperclip, can cause their rhythm to fall out of sync. One tick at a slightly different rate than the other, simply because one is closer to Earth's gravitational pull than the other. We're talking millimeters here. The thickness of a credit card and time itself bends. The implications are not merely academic. These clocks are sensitive enough to challenge the very assumptions we've long held about our universe. What we once called constants, like the speed of light or Planck's constant, may not be as constant as we believed. And that frightens the scientific community not because the clocks are broken, but because they are too perfect, too exact. The instruments we created to measure reality have started to expose the cracks in it. At the forefront of this revolution are optical lattice clocks from institutions like JILA and NIST. These aren't just better versions of old atomic clocks. They're something else entirely. Machines so advanced, so tuned to the very breath of reality, that they would lose less than a second over 30 billion years. That's longer than the universe has even existed. And yet, when two of these clocks were placed 1 millimeter apart, their time began to diverge. Einstein's theory of general relativity had predicted this. It wasn't new, but the scale was. For decades, relativistic effects were observable only over vast distances, mountaintops versus valleys, satellites orbiting far above the Earth. But now these differences were measurable on a desk. Two identical clocks, one placed atop the other, time split in half by a sliver of space, a vertical fracture in the flow of the universe. Imagine what this means. Your fingertips might be experiencing a different pace of time than your wrist. A single breath, a heartbeat, now carries layers of complexity we never dreamed of. And if this discrepancy exists at the human scale, what happens when we zoom in further? What happens when we approach the quantum realm, where gravity and quantum mechanics refuse to play by the same rules? The boundaries between time and space, between certainty and uncertainty, begin to blur. These are not thought experiments anymore. These clocks have real-world consequences. GPS systems rely on relativistic corrections. If they didn't, your phone would guide you miles away from where you stand. High-frequency trading, where billions are won and lost in nanoseconds, depends on perfectly synchronized timing. Even quantum computers rely on temporal precision to maintain coherence. But now that precision is revealing something far more unsettling, something we may not be ready to face. In Germany, at the Physikalische Technische Bundesanstalt, PTB, scientists have developed a new clock, a crystalline marvel using elements like indium and ytterbium, reaching 1,000 times greater accuracy than the cesium clocks we've trusted since 1967. If this clock had been ticking since the birth of the universe, it would be off by less than a second today. That's not just a milestone. That's a redefinition of time itself. And so the second, the unit we've used to measure every moment, every life, every orbit and explosion, may soon be rewritten. Not in decades, but now. We're transitioning from microwave-based measurements to optical ones. A leap not just in technology, but in our very understanding of reality. Yet every breakthrough uncovers something darker. Because with this newfound precision, scientists are discovering inconsistencies, irregularities in fundamental measurements, signs that perhaps the universe is not as stable or uniform as we believed. Time, when measured to 18 decimal places, begins to shimmer. It dances with the invisible, with quantum foam, with dark matter, with forces we've never seen but that have always been there, lurking in the fabric of the cosmos. The terrifying truth is that as our measurements get better, our certainty gets worse. And then came the nuclear clock. In September 2024, scientists achieved what had previously been deemed impossible. They measured the thorium-229 nuclear clock at optical precision for the first time. Unlike traditional atomic clocks that monitor electron transitions, this nuclear clock looks deeper, into the very nucleus of atoms. It is astonishingly resilient, immune to the fluctuations of temperature, magnetic fields, and other external noise that plague lesser machines. It could become the most stable timekeeping device ever built. But this isn't just a better clock, it's a window, a portal into the unknown. It might detect forces we've never encountered, anomalies at the quark level, or signals from the dark sector of physics that interacts only through gravity and uncertainty. It could reveal the fingerprints of the universe's hidden architecture. Dr. Eckhard Peak from PTB put it plainly. These comparisons could uncover entirely new laws of physics. And it's already happening. Back in 2020, researchers at MIT stumbled upon something strange while comparing isotope shifts, a deviation that didn't make sense. It looked for a moment like a fifth force had been discovered, a hidden interaction beyond gravity, electromagnetism, and the nuclear forces. Though the anomaly was later attributed to a variation in nuclear structure, not new physics, it showed just how sensitive these measurements have become. Sensitive enough to brush against the limits of our known reality. Even a false alarm in this context is a revelation, because it proves the clocks are capable of seeing things no other instrument can. But now they are being turned toward the most elusive shadow of all, dark matter. Now the clocks are no longer just telling time, they're chasing shadows. The kind of shadows that stretch across galaxies, yet slip through every telescope. Dark matter. Unseen, undetected, but possibly not for much longer. In January 2025, a bold new collaboration began. Scientists from PTB and the University of Queensland linked ultra-stable lasers across continents, fiber optic cables, GPS satellites, a global web of atomic timekeeping. Their goal was simple, but staggering, to catch dark matter in the act. If ultralight dark matter truly ripples through space like a shifting field, then even the tiniest changes in time, nanoseconds out of place, could expose it. By comparing identical clocks spread across vast distances, scientists hope to see oscillations, a tremor, a pulse, a glitch in the constants of nature. So far, they've found nothing definitive, but even that is meaningful, because nothing still narrows the search. Whole theories of what dark matter could be are being ruled out. Slowly, like peeling back layers of fog, the truth is coming into focus. And every passing second, these clocks are refining that search. But behind the excitement, there's unease. John Year, one of the lead physicists at JILA, admits it softly. Physics is not complete. It's not an admission of failure. It's a whisper of warning. For decades, gravity and quantum mechanics have coexisted awkwardly. Two great pillars of science that refuse to unify. But these new atomic clocks, they've begun to push the two into direct conflict. With their near-perfect sensitivity, scientists are now watching for gravitational redshifts at the nanoscale. They're not relying on theories anymore. They're testing them in real time. What was once buried in math, hidden in the chalk dust of blackboards, is now visible in a machine no larger than a suitcase. And then comes the most unsettling thought of all. If the nuclear clock proves sensitive enough, and early results suggest it might, it could do more than measure time. It could detect space-time itself, trembling, fluctuating, breathing. Not the smooth, flowing continuum we've always imagined, but something granular, broken into quantum fragments. The very structure of the universe, shimmering like static on an untuned screen. And what happens if it confirms that? What if time itself is just an illusion, an emergent property of something deeper, stranger, and far more fragile? That question is no longer philosophical. It's experimental. The clocks are forcing us to look, forcing us to ask, what is time really? And perhaps, more importantly, what happens when it breaks? What comes next isn't just about clocks. It's about everything that depends on them. Our navigation systems, our financial markets, our defense technologies. All of it runs on precision. All of it assumes time is stable. But if these clocks are revealing that time itself is slipping, even by a fraction, what does that mean for us? The redefinition of the second already underway is just the beginning, a tiny adjustment in a unit we take for granted, but it shakes the foundations of science, industry, and reality. Soon, atomic clocks may be placed not just on satellites, but on the moon, Mars, deep space. We are turning the entire solar system into one enormous experiment, a cosmic lab stretched across millions of miles, all synchronized to a beat so precise, even the slightest irregularity could unravel a new law of physics. And so far, the clocks haven't contradicted physics. But that's exactly what worries scientists, because they're getting too close. There's nowhere left for new physics to hide. Every decimal place adds pressure. Every confirmed result leaves less room for the unknown. That edge, the narrow space between certainty and chaos, is where the future of science now lives. And perhaps the most haunting truth? The fear isn't that the clocks are wrong, it's that they're too right. They reflect back the universe exactly as it is, not as we hoped it would be. They show us a reality more fragile, more dynamic, more mysterious than we ever imagined. Time is not a constant march. It's a trembling thread. And now we hold it in our hands. If you thought clocks just measured the hours of the day, think again. They may be counting down to something far bigger, something we're only beginning to understand.